All right, so a really common question in statistics would be something along these lines. We have 430 people at our school, and we want to know what percentage of them think Mr. Blackburn is a good teacher. But we don't want to survey all 430 kids at the school, so maybe we take a sample of 80 kids. And we find out that the sample proportion is, I don't want to say a number and embarrass myself. Let's say it's 30%, hopefully, at least. The question is, how good of an estimator is this for the true population proportion? So this type of thing happens a lot in statistics. We want to estimate a parameter using a sample statistic. So how good is this sample? How likely are we to be off? And how far off are we if we are off? To answer these questions, there are statisticians that have developed confidence intervals. So that's what this chapter is about. Section 8.1 is going to lay out the groundwork for confidence intervals, and then 8.2 we're going to learn how to calculate confidence intervals for proportions. And then 8.3 we're going to do confidence intervals for means using X bars. All right, so recall from previous coursework that a point estimator is a statistic that provides an estimate for a population parameter. In this case, this was my point estimator. The value of the statistic from a sample is called the point estimate. All right, let's be a little more specific. P hat is the point estimator for P, and this 0.3 was a point estimate. In the last unit on sampling distributions, we always had the true population parameter when we did the problems. In reality, that is never going to happen. In reality, we only have the sample data and 1 point estimate. How smart are we really? Example. For your end-of-year stat project, you want to estimate the average IQ of the senior class at the John Cooper School. In order to do this, you take a simple random sample of 16 seniors and have them take an IQ test on an iPad. After collecting data, you find that the average IQ was 115. So I'm giving you guys, this is made up data. I'm giving you guys the benefit of the doubt and saying you guys are kind of smarter than average. In general, IQs are kind of centered around 100 on average. Is 115 a parameter or statistic? Let's read here. After collecting your data, you find the average IQ to be, so that sounds like that's the average of the 16 seniors. So that would be an X bar. And that is a statistic. What is your best guess for the value of the true mean IQ of seniors? Well, I don't know about the best guess, but this is our only guess. So 115 would be our best guess. This is your point estimate. How confident are you that this estimate is exactly correct? Well, how confident are we that the true mean is 115.00000000000 with an infinite number of zeros, exactly 115? I would say we are very confident it's not 115, right? It's not going to be exactly 115. The question really isn't a matter of whether it is 115 or not. The question is, how close is it going to be to 115, right? Why might it be incorrect? When we sample, I guess we get sampling variability. I mean, that's kind of a stupid statement. Sampling variability. Sorry, I could word this a little more gracefully, but when we take a sample and we repeat our sample, and we do another sample, each time we're going to get sample statistics that are slightly off. So that's just random chance. While this point estimate is our best guess, it gives no indication about how close this estimate is likely to be to the true value. If we estimate the population mean IQ to be 115 and this estimate may be off by 3 IQ points, that's one thing. But if it's off by 30 IQ points, that would be something completely different. Therefore, there becomes a practical need to let people know how close these point estimates are likely to be from the true parameter. In statistics, we construct confidence intervals to give a range of plausible values that the true parameter is likely to be within. For example, we might say something like the population mean IQ of JCS seniors is probably between 110 and 120. For instance, this would be a confidence interval. It's better to report an interval than a single value. You tell people a single value, they're going to think the average is exactly that. And it's not. You give them a range of values, and they're like, okay, yeah, it's probably somewhere in here, and I can kind of look at it and get a min and a max idea right off the bat. So this is better. So it's going to be hard for us to do this activity on the, like in a video. It's something we did in class, but I'll just walk you through it kind of. First, let us pretend that the IQ scores for JCS seniors are approximately normal. First assumption. And further, let's pretend that the population standard deviation is 10. Second assumption. You do not know the population mean. I'm going to pretend that I know the mean, and I stored it in my So what I did was in my calculator, I stored a variable called the IQ. I can click it, but I don't want to hit enter. So if I hit enter, it'll show you what that number, what the IQ is. So this is the true mean IQ of JCS seniors for pretend. Like I said, I just made it up. The following command will simulate drawing a sample of 16 seniors from a normal population with a mean of IQ and a standard deviation of 10. So the command is random normal. It'll give me 16 numbers, and then this is the mean and this is the standard deviation. So I'm going to run one. If I go rand norm and I put in my IQ, or the average IQ of seniors, and then I put in 10 for the standard deviation and I put in 16, it will randomly generate 16 different numbers. So this would represent each student in my sample. So the first kid had 105, 120, ooh, smart kid there. 99, oh, little, not as smart, I don't know, awkward topic, sorry. Now if we use the mean command, it'll calculate the average of that list. So I could just embed the sample inside the mean and it'll give me my average. So if I say mean, oops. So if I'm just going to go up here and grab this and then type the mean. So what this will do is it'll generate a sample of 16 and then it'll calculate the average. So I hit it once, I get a 105.3. So we didn't do that like this in class, but I'm going to do it here. So I'm going to plot that 105.3 right here. Oops, I don't want that dot. 105.3. Now if I hit enter again, it's going to generate another sample of 16 and calculate the average of those 16, 101.7. If I do another one, 100.6. You guys might wonder why I'm graphing them like this. 100.3, 103. In fact, what we should be doing, 100, man, why are these so low? I don't remember what I put. Actually, I don't remember what I put in for the average. I thought it was like 110, but it's not looking like it, is it? Well, or is it, right? Maybe we're just getting unlucky. We only did 5. It's not the law of 5 numbers, it's the law of large numbers. 102.6, 102.9, 104.7, 111 there. I want to get one that was a little higher. 111. What was some of these other ones? 102, 104, whatever. Doesn't really matter. 102, 104. All right. Now, normally we would make this as a dot plot. We'd drop these values down, and that would actually create a sampling distribution of X bar, just like we studied in the last chapter. Okay? But I want to do something a little bit different with these. What I want you to, well, what I told the kids to do in class was use your knowledge of the sampling distribution of X bar and the sample mean I give your group to construct a confidence interval that is likely to capture the population mean. So when we did this in class, what some kids did was they kind of just said, well, I don't know, maybe. So what I did was I only gave them one mean. Each group got one mean, and they didn't see the other ones, So what they did was they'd take their mean and they'd come up with some kind of intervals. Well, I know it's not 104. Maybe it's, 100 and I don't know, what would you do with 104? Some kids literally just said, I'm going to just add 10. 114 to 114 to be up here. and then I would subtract 10, 94. Some kids did stuff like that. Other people said, I'm going to add 5, or and some people just did it haphazardly. I was hoping people would put a little more thought into it. I said, use your knowledge of the sampling distribution of X bar. After all, these points are described by the sampling distribution of X bar. It's centered about the true population mean. But I only have one point estimate. I don't even have all 7 of these. Normally we just have one estimate we have to look at. What about the spread? This is kind of the key value. The standard deviation is the standard deviation of the population over the square root of n. In this case, it's 10 divided by the square root of 16, which is 10 over 4, which is 5/2, which is 2.5. So 2.5 is the average distance that your X bars would be from the mean. So some more thoughtful groups said, well, I'm going to add that 2.5. I'm going to take this value and I'm going to add 2.5 to it, and I'm going to subtract 2.5 from it, which is pretty smart. The problem is we kind of also know that this sampling distribution is normal, or approximately normal. Well, if it's approximately normal, you're only going to be within one standard deviation of the mean 68% of the time. So there were a couple groups that kind of said, if I want to capture the mean more often, maybe I should go 2 standard deviations above and below the mean. So if we multiply this by 2, we would get an interval of 5. And they said, I'm going to take this 101 and I'm going to add 5 to get it to 106. And I'm going to subtract 5 to get it to 96. Did I do that right? I think so. Whatever. So we all kind of had our intervals. Some of them were more narrow. Some of them were longer. And then we got one here too. Most of them though were centered about their sample mean. Why would you go further above or further below? Actually, one group did. They kind of said they thought that theirs was high, so they kind of went a little bit above and way below. But I mean, why would you think that? If you think that, then why even take a sample if you think you know what it is already? So then what we did kind of at the very end was we actually showed the class what the real IQ was. So this is the real IQ, for this activity, the IQ, the true mean. It was just 105. So we did get a little bit unlucky with our samples. The true value was 105, so it's right here. And then we kind of played around with it and we said how many people caught the average. And there was a couple people that had a really narrow interval that didn't. And these people that had a really huge interval, most of them captured it. And then we just had some discussion about it. But really, this thought process here is exactly how we calculate confidence intervals. We consider the shape. We look at the standard deviation of the sampling distribution of the statistic. And then if the shape is normal, and this is the standard deviation, if I want a 95% capture rate, I simply multiply by about 2, and that's going to give me an interval that's going to capture it about 95% of the time. I'm going to miss it sometimes. Every once in a while I'm going to get a bunch of smart kids, and I'm going to miss it above. Or I get a bunch of other kids, and I miss it below. Okay? But this should only happen 95% of the time. So if you want to be about 95% confident, you should find the standard deviation of the sampling distribution of X bar, multiply it by about 2 to get 2 standard deviations, and add and subtract it from your sample mean to get your interval. That is exactly how we calculate confidence intervals. Note, this method will only be accurate if the sampling distribution of X bar is approximately normal. What do I mean by accurate? Well, what I mean by accurate here is that it's going to capture 95% of the time. If my sampling distribution isn't approximately normal, my sampling distribution looks like this, then when I go 1 standard deviation above and below, I might miss more than 5% of the time. Suppose I got a sample mean of 1